Okay, we're starting on one of the more important applications of the use of differentiation. Now consider this function, this quadratic function, y equals to 7x squared plus 35x minus 31. Now for part A it's easy, right? Because we've learned all this before. Here's the answer. But the key of this question is all about part B. Okay, now here's the dy dx and here's the y, the original function, and you have to tell me on which interval of x the function will be decreasing or increasing. Now, how in the world do we find that if we don't have the graph, if we don't have the sketch of the graph? Okay, but for now, I will show you the graph so that we could better understand the concepts behind it first. So for the time being, if you just look at the graph here, very obviously, the answer to B1 would be all the x's less than or equal to negative 2.5. And likewise for B2, the answer would be all the x's greater than or equal to negative 2.5. Okay. However, if we don't have this graph, how do we make use of dy dx to find the answer here? Okay. Now, remember when we are talking about when the function is decreasing, that means its slope is negative. Why? If we look at here, this is at these places, right? The function, the curve is decreasing, okay? It's going down, so the slope is negative, okay? Right? And so for these values of x in the derivative, it must be less than 0 all the way. These are all negatives up to when x equals to negative 2.5. Okay, so what happens when x equals to negative 2.5? The slope here would become a horizontal line, right? The tangent line would be a horizontal line, which means that the slope will equal to 0 when x equals to negative 2.5. Okay, so if we keep going to the right of that point, you start to see that the slope of the tangent lines at each point, okay, are positive, okay, because it's obviously increasing. So all these places, the slopes are positive, okay? So in other words, to see which part of the function is decreasing or increasing, the first thing is we find out the vertex, the vertices of the function. In other words, there's a special name for it. Okay, we call these local extremum. Okay, the plural form would be local extrema, and in this case, for this vertex, you call that a local minimum, and it is this point that divides the function into two sections. So to the left of the local extremum, that is x less than or equal to negative 2.5, the function is decreasing, right? And f prime of x would be less than 0 because the slopes are negative, right? So on the right hand side of negative 2.5, it would be the function itself would be increasing, right? Because it's going up, and the derivative f prime of x would be greater than 0. Okay, so this is just an illustration. So how do we write this out? So for part B, first I want to find where the local extremum is. So I set dy dx equals to 0 because this is where the slope is always equal to 0. It's a horizontal tangent line. So 14x plus 35 equals to 0, and so of course x equals to negative 5 over 2. And then what we do is we will draw this, write out this table here. Okay, so in the middle, this is when x equals to negative 5 over 2, and of course the slope would be equal to 0 here. And for x less than this, okay, if you just put a random number in this interval, say negative 1000, you plug this into your derivative. Okay, if I sub x equals to negative 1000, okay, the derivative is obviously negative, right? Likewise, if you put in, say, positive 1000 into the derivative, okay, your dy dx would be positive. Okay, and so the function is decreasing on x less than or equal to negative 5 over 2, and the function is increasing on x greater than or equal to negative 5 over 2. Remember, we put less than or equal to, and here greater than or equal to, because when x equals to that number, you can say either it's decreasing or increasing. Okay, so